we discussed the weak form term by term and kind of tracked the corresponding terms in the algebraic equations that you would get. Let's put it all together. If you do that, you'll get the equation shown here. And this is this equation I showed before when talking about going from the weak form to the algebraic equations. And now we have a better idea of, the genealogy of each of these terms. So we know that when we do the integration over there, we can find out what these coefficients are. We know that from the integrating the source term, we will get these terms here. Okay, and that'll come into the, that'll multiply all the weights at the nodes. And for this term here, when I evaluate it at the right boundary, I will get this term here. And then when I evaluate it at the left boundary, I'll get this term here. As I've talked about before, these weights are arbitrary, so we want this to be satisfied for any arbitrary choice of the weights, and the only way we can do that is to set each of these to be 0 individually. So we have to set this to be equal to 0. That'll give us the equation at node 1. Similarly, that to be 0, and that'll give us the equation at node 2, and so on. And you'll get the set of equations shown here. So that's the equation at node 1, this is the equation at node 2, this is the equation at node 3, and that's the equation at node 4. And if I look at the stiffness matrix form based on these coefficients here, I will enter them in the corresponding rows and columns of the stiffness matrix. For instance, this would go into the first row, first column, this coefficient of the stiffness matrix. And these terms here would go into the right-hand side, the force vector. So for instance, this whole term here would be the first row of the F vector. One thing we haven't talked about is the temperature boundary condition that we have at the left boundary, how to incorporate that. So we'll discuss that before talking about how then the solution proceeds. Let's look at that.